Okay, this should work. So, hi everybody. My name is Andrea Del Prete. I'm a professor at the Industrial Engineering Department. And this class is going to be about how to control legged robots using numerical optimization methods. So let's first get rid of the logistic information. I've created a classroom website for this course. I suggest you to copy that code because that's going to be needed for you to subscribe to the website on Classroom. I'm going to use the website for communicating with you and for giving you the material. There is already some material because I don't know, maybe you know already, but associated to each classroom website, you have a shared folder on Google Drive. And in that shared folder, I will upload all the material for this course. So the course is structured in two parts. The first part is about doing reactive control using numerical optimization. So we're going to start actually from the modeling part, in case you don't know how robots are modeled. We're going to spend roughly 1 hour talking about that. So a quick review of robot kinematics and dynamics. Even though that's not really our main interest in this course, is assuming that you have a model, how do you then control the system? That's more what we are interested in. Then we're going to talk about doing control in joint space. So assuming that you know exactly how each joint of the robot should move, how can you do control? Then we're going to move to task space. So assuming that you want to control not directly the joints of the robot, but a given function of the robot state, such as the center of mass, which is very important for walking, or the position of the feet, which again is a very important part of walking. Then we're going to move to the more pragmatic side of this course, which is how to implement this. So we're going to spend 1 hour doing an overview of the implementation still using slides. And then we're going to spend 2 hours actually working on the code. I'm going to give you more details on the code in a moment. The second part moves from reactive control to walking trajectory generation. So reactive control is good as long as you know exactly how you will like to move. But when it comes to walking, it's not so easy to figure out what is a feasible walking trajectory for your robot to track. So in the second part of the course, so the last 2 days, so roughly, this is going to be today and tomorrow. And the second part is going to be Wednesday and Friday. Thursday, there is no class. So in the second part, we're going to discuss how you generate a reference trajectory that you can then track using the methods that we developed in the first part. So we're going to introduce the so-called linear inverted pendulum model, which is a simplified model that has been widely used for generating walking movements. And we will see then how we can use this model, which is very simple. It's a linear model, as the name suggests, to generate a trajectory for the center of mass of the robot, which we can then track using a reactive controller. And as before, we will spend 1 hour giving an overview of the implementation using the slides. And then we're going to spend actually another hour for coding, the trajectory generation part, and then 2 hours for integrating what we did in the second part with what we did in the first part. So overall, it's quite a lot of time spent on the coding and looking at the implementation. So it's a quite hands-on class, I would say. Many of you have already taken my course on optimization-based robot control. So Matteo has, Gianni, Riccardo, Elisa. So for you four guys, the first 3 hours, no, sorry, the first 6 hours should be mainly a review, because I've already covered most of this in my class. For U3, no, it's all brand new. Okay, let's discuss quickly how you would handle the coding part, because that's the most technically challenging, I would say. And I would like you to start preparing for the coding possibly today, because starting from tomorrow, we need to start coding, so you need to be ready. So I prepared a Docker image, which you can find at this address. In case you don't know what Docker is, it's a virtualization tool that allows you to simulate a certain OS on your machine. So this is going to work regardless of your OS. I'm using it on Mac. If you have Ubuntu, of course, it's going to work because it's an image of an Ubuntu machine. And even if you have Windows, you can use it under WSL 2, possibly, so the Windows subsystem for Linux. And this is my recommended option for coding in this class. Because if you use this Docker image, you will have all the necessary libraries that are already installed. Okay. And so you will not need to do any installation or setup of environment variables to make things work. So that's my number one option. In case you have an Ubuntu machine, and maybe also if you're interested in using this software even after the end of this course, then your best option would be to install everything natively on your Ubuntu machine. And that should be quite straightforward because all the libraries are provided as Debian packages, which means you can just do sudo apt install with the right library names, and you should be ready to go. Well, there are a few extra steps, but so in both cases, okay, yeah, it's here. In both cases, you can find detailed instructions on how to configure everything in the shared folder that you will find on Classroom. So subscribe to Classroom, access to the shared folder. There will be a GDoc file called installation instructions. Follow those instructions and you should be good to go. Okay. So probably you two guys have already everything already on your machine because you have used TSID, and that's the main dependency. So if you have TSID up and running on your machine, you're good. Well, you also need Kazadi, but pip install Kazadi should do it. Okay, any question on this?
I mean, for now, the Google Drive folder is empty. Is it?
No, it's not normal. Let me.
Maybe it's. I don't know.
No, and sometimes the shared folder has some troubles. So it should be this one. I don't see it empty. How did you go to the shared folder? Because I don't even see it here.
Yeah, me neither. But no, I went to Google Drive Classroom and I already have the folder. But I don't think maybe it's not the same one.
So let's.
It shouldn't be the same.
Let me do this.
Yeah, if you can share the link, maybe I suppose.
You all have a Unitian account, correct? Okay, so I'm gonna share it with all Unitian people. And then I'm gonna copy paste the link to the shared folder here. So if you access this, you should see I've already uploaded the installation instructions and the slides of today and tomorrow. Okay. So before we start delving into the math, I've prepared a few videos to show you a bit of some remarkable legged robots that history has seen. So there in the top left, you can see the first humanoid robot ever developed. It was in 73 in Japan. I don't have a video of that, unfortunately, I just have that picture. Then top right, you can see the MIT Leg Lab. They were making this wonderful monopod hopper robots in the 80s. And by the way, that lab was run by Mark Rybert, which then became the founder of Boston Dynamics, which probably you have heard of. So you can see there the monopod hopper evolved into a biped hopper, which still works in a two-dimensional world because it is attached to the ground through this bar, but it can do some pretty impressive stuff. And now they freed it from this bar, and they made it walk and jump in 3D, doing somersaults. Yeah. And then they moved to quadrupeds. Probably this is the ancestor of Big Dog, the first robot from Boston Dynamics. This is a bounding gate. A very inefficient gate, if you ask me, but then moving on here, moving forward of up to 20 years, early 2000, we can see the first running humanoid robot. Jumping on one leg. Might seem trivial because we can all do that, but trust me, doing that on a robot, it's super difficult. And here are more recent examples. Top left, again, MIT, but much more recent. This is probably 2016, something like that. It's another quadruped robot, is the MIT Cheetah, which was very innovative for those years, and actually more or less all the quadruped robots that you can see nowadays, which are everywhere, they are inspired from this robot in terms of hardware design. Because basically these people had the idea of using much larger motors and using much lower gear ratios, which makes the control of the actuators much simpler because you have much less friction. And that turned out to be a winning move to making this system behave nicely in the real world. So the robot is detecting the obstacles using probably a laser scanner, and is figuring out when to jump and how to jump in real time. Using everything is done using numerical optimization techniques. So it's quite similar to what we're going to see in this class. So nothing is pre-computed, everything is evaluated online. And here we have a more local example of quadruped robots. This was coming back. This was designed and built in Genova at the Italian Institute of Technology. It's called HiQ, hydraulic quadruped. So contrary to the previous one, this one is I think it's completely hydraulic, or maybe it has 2 out of 3 degrees of freedom of the leg, which are hydraulic, and one, the yaw, which is electric, but that's kind of a detail. And hydraulic robots are extremely powerful, so they're very good for doing extremely dynamic movements. And indeed, also the Atlas robots, which probably you have already seen by Boston Dynamics, is mainly hydraulic. I don't know if it's completely hydraulic, but for sure it's mainly hydraulic. And that's how you can achieve these super dynamic movements. So this was in 2017, and if you go on YouTube and look for Boston Dynamics Atlas, you can find even maybe more interesting videos than this one of this robot doing crazy movements.
Now, everything doesn't go exactly the way it's supposed to.
So you can see that even the Atlas robot sometimes fails. You rarely see these kind of videos on YouTube, but they do exist. Just to show you that it's not that easy even for the top people in the field.
But may I ask, what is the difference between the models from the 80s up to today? What's changed? I mean, you saw some quadruped robot back there.
It depends. It depends on the kind of robots. So quadrupeds, they mainly have evolved in the direction I just described. So using bigger motors, which allows you to have smaller gear ratios because the motor has more torque. So you don't need to multiply it by a lot to have the torque that you desire at the joint. And having smaller gear ratios, you have much less friction. And less friction means it's easier to control the system.
So it's mainly on the hardware aspect. And
on the hardware aspect, yeah. I was thinking you were asking on the hardware aspect.
I was mainly focusing
on the control.
Yeah, perspective.
On the control, well, that's the subject of this class, so I will tell you in the next 12 hours. Okay, well, and then there was just a slide showing some inspiring pictures on possible applications for legged robots. Why it's interesting to study and develop legged robots compared to wheeled robots, because of course wheeled robots are much cheaper in terms of hardware. They're much more stable, less dangerous, easier to control. So they win on many aspects. But the reason why legged robots are interesting is because they allow us to have robots that go in the same places where humans can go. So they climb there, they can walk in a disaster scene after an earthquake or a wildfire, and they can be used in basically any kind of environments where humans can access. You can use a humanoid robot, and the same is not the case for wheeled robots. So they're much more flexible and versatile, but the cost to pay for that is expensive and fragile hardware, much less stability because the robot can fall down at any moment, and a much more complex control method as well, which is why we need classes on how to control legged robots. Okay, so let's go back to the slides and let's start talking about modeling. So I'm not going to directly jump into how you model a legged robot because that's a lot of stuff. We're going to start on modeling robot manipulators, which are simpler. Then we're going to see how that model needs to be extended when the robot comes in contact with the environment. And then we're going to extend that to legged robots, which are, again, one step further in terms of modeling. So let's start with some basic notation. I'm going to call the state of the robot with the letter X, the control inputs of the robot with the letter U. That's very classic notation from control theory. The identity matrix is going to be I. The zero matrix is simply going to be a 0. Sometimes when needed, I'm going to add as index the dimension of the matrix. So I3 means identity matrix of size 3 by 3. You will often hear me say that a system is fully actuated or a system is underactuated. So let me clarify what I mean by that. By fully actuated, I mean that the number of actuators of the robot is equal to the number of degrees of freedom. So a robot manipulator typically is fully actuated because you have one motor at every joint. So no problems there. Underactuated is when instead the number of degrees of freedom is greater than the number of actuators. And that's going to be the case for basically all mobile robots. So cars, UAVs, legged robots, underwater robots, all robots that can move around typically are underactuated. And that will become more clear when we talk about the modeling of legged robots. Okay, so let's discuss how you model a robot manipulator. So for robot manipulators, these are systems that are attached to the ground or to a table or to a structure, whatever, which makes their base fixed. So the base doesn't move. That's the assumption. So we're gonna represent the robot as a sequence of links, so rigid bodies, which are attached to each other by joints. So the joints are the points basically where this around which the system can rotate. And the way we represent the configuration of a robot in space is by measuring the angle at every joint of the robot. So you can see here the first angle of this robot is basically measured by the angle between these two lines. And then we have the second joint, which measures this angle, and the third joint, which measures this angle here, Z. So if you collect all the joint angles in a vector, you get the configuration vector, which we are going to call Q, which contains all the relative joint angles. However, typically, knowing the joint configuration is not enough to represent the state of the robot. You also need the joint velocities. And well, for a robot manipulator, the joint velocity vector is very simple. It's just the rate of change of the joint configuration vector. So we just measure how quickly the value of the joint angles change in time. The time derivative, basically. The terminal part of the robot is typically called end effector. I'm going to use that term a lot. Here is called end flange, but I don't say end flange, I say end effector. Actually, everybody says end effector. I don't know why it's written end flange there. Okay, how are these robots actuated? So typically you have one actuator at each joint. That's why they're fully actuated. However, the actuator can be of different kinds. You can have electric, which is the most common in robotics, but you can also have hydraulic or pneumatic. Hydraulic is also common in cases where you need a lot of power, because hydraulic actuators are the most powerful and the most dynamic ones. That's also why they are the most dangerous. So you need to be very careful if you're working with a hydraulic robot, because it can kill you quite easily. I've worked with them, so I know I should be scared. And it's important that we discuss a little bit about actuators, because depending on which actuator your robot has, you might decide to model them differently. Because actuators can be modeled either as a source of velocity, a source of acceleration, or a source of torque. Well, we might have also other options, but these are the most common three. And which option is the most suitable? It depends on your actuator type, and it depends on the application. So same robot, depending on the application, you might be better off using option number 1 or option number 2. So choosing the right model for your actuator is also a bit of an art, more than a science, because it boils down to knowing what is a reasonable approximation for the problem you're trying to solve. So let's discuss the different options. Option number 1, which is the simplest, is to assume that your actuator can directly provide a desired velocity. That's the assumption that typically people do in the industry when they're controlling robot manipulators. They assume that the robot can basically generate whatever velocity at every joint instantaneously. So I tell the robot, move at 1 radian per second in this joint. It does it. Then I say, move at -1 radian per second, and it immediately switches the velocity from 1 to -1. Of course, that's an approximation of reality, because in reality, the velocity cannot change instantaneously from 1 to -1. You're always going to have a transition phase. But the point is that transition phase so fast and so reliable that I can neglect it? And if the answer is yes, then you can model your actuator as a velocity source. If the answer is no, then probably you need to look for other options. So this hypothesis tends to work very well if you have a hydraulic actuator, because hydraulic actuators are so powerful and so dynamic that they can change the velocity almost instantaneously. So you might end up having a good model with a hydraulic robot. It could also be good for electric in certain conditions. So mainly if you're not moving heavy weights, or you're not making contacts with large forces. And that's not the case we are interested in, because for legged robots, we are making contacts with large forces because the robot needs to sustain its own weight. So if you model your actuators as a source of velocity, then your state is simply the Q vector containing the joint angles, and your control inputs are the joint velocities. And your dynamics is simply an integrator. So the rate of change of the state, which is Q, is simply the control inputs U, which are the joint velocities. So very, very simple. Unfortunately, we cannot work under that assumption. So the second option is to model actuators as sources of acceleration. This is good for electric motors, electric actuators, without large contact forces. So in this case, if your control actuators are generating acceleration, you also need to model the velocity inside the state of your robot. So the state now is extended to contain both Q and V, joint angles and joint velocities. And your control inputs to the system are going to be the joint accelerations. Even in this case, the dynamics is linear, but instead of being a single integrator, it's a double integrator. Still very simple because it's linear. Unfortunately, we are not going to use that assumption, because this is good if you don't have large contact forces, or you don't care about the contact forces. we're going to fall into the third category, because we have large contact forces we do care about, which is modeling actuators as a source of torque. I say torque because actuators are typically for revolute joints, so they need to provide a moment, not a linear force. But if you had a prismatic joint, this would be a force, of course. So this is good for electric motors without high friction gearboxes. So this is something I already mentioned when talking about the hardware design of modern quadruped robots. If you have a high ratio gearbox, so a gearbox with a gear ratio that is above 20, I would say, most likely it's going to have a high friction, especially static friction. So the frictions that you have even at tiny velocities, it's the one that prevents you from moving. And when you have that kind of high friction, then it becomes very hard to control the torque at the joint of your robot. Because even if you apply a torque at the motor, that torque is going to be detracted from the friction torque. So if the torque is smaller than the friction torque, you have no motion at all. And if the torque is higher, the torque you see at the output is the torque you apply, generate, minus the friction torque. The problem is that this friction torque may depend on the position of the joint. It may depend on the temperature of the robot, the temperature of the environment, the humidity of the air. So it's something that you cannot really model well. You can trust me on that because I've tried for years to model it and I failed miserably. So your best option if you want to use torque control is to use low gear ratios. So from 2 to 10, that's a good range where you typically have low friction. And most quadruped robots these days fall into this category. So they have low gear ratios, so low friction, which means that the torque that you generate at the motor is very similar to the torque that actually goes into the joint. So the state of the robot is always as for the case of acceleration inputs. So you have the joint configuration Q and the joint velocity V. But this time the control inputs are no longer the accelerations, but the torques, which means that your dynamics is no longer a linear system, but it becomes nonlinear. So this expression, if you have never taken any class on multi-body dynamics, is going to look completely alien to you, but don't worry, I'm going to walk you through it. So this you can think of this expression as an extension of Newton's second law. So Newton's second law would be ma equal F. So mass times acceleration equal to the force. So now instead of having a force, we have the torque generated by the motors. Since we have rotatory joints, we don't have a force, but we have a torque, a moment. The mass, which was a single scalar value in the case of a single rigid body, now becomes a matrix with the name M, and this matrix depends on the joint configuration Q. So M is going to be a matrix of size NV times NV. NV, if you don't remember, is the size of the vector V, so the number of joints of your robot. This matrix is positive definite, which is the equivalent of being positive for a scalar. So in the scalar case, the mass of a body cannot be negative. Of course, you cannot have a negative mass. And in the multi-body case, the mass matrix cannot be non-positive definite. Then we have the accelerations, V dot. That's the same of A. That's the derivative of the velocity, gives you the acceleration. And then the main difference, I would say, between the multi-body case and the single body case in terms of dynamics comes from this term here, which is the term which I called bias forces. So it contains all the forces that are due to Coriolis, centrifugal, and gravity effects. Okay. And those depend on both the joint configurations and the joint velocities. So that term depends on Q and V. So this, it's a NV-dimensional nonlinear differential equation, which describes the relationship between the joint torques, which are generated by your motors, your actuators, and the acceleration of the joints. So if you know all the dynamical parameters of the robot, so you know the geometry, and you know each link of the robot, its weight, its center of mass, its inertia tensor, then there are softwares that allow you to compute all the terms in this expression. So you can compute M and you can compute H, because actually those are the only two terms that need to be computed. Okay. So we are not going to work on how to compute these terms, because we are going to use a library called Pinocchio, which is already installed in the Docker image, which has functions for computing these terms for us. Okay. And this computation is very fast. Okay. It takes microseconds. So it's not a problem computing these quantities nowadays. It was 20 years ago, but nowadays it's super easy. Okay, the bias forces, as I told you, contained terms depending on Coriolis, centrifugal, and gravity forces, which could be written also in this form by splitting the gravity term, which depends only on the joint configuration Q, and this term here, which you can see is, it's not really, it's quadratic actually in the joint velocities. You cannot see it in this form, but you can write this in a form that makes it explicit its quadratic dependency on the joint velocities. But we're going to work for the rest of the course using H. So this is just for your information, but we don't need this. Okay. Then we can write the dynamics of the system in classic state space form. And if we write it in state space form, we get this kind of expression where we have the first row that defines the dynamics of Q. The dynamics of Q is trivial because Q dot is equal to V, which is part of the state. And then the second row defines the dynamics of V, which contains the real multi-body dynamics. And this way of writing it makes it explicit that we have a linear dependency on U, because U appears linearly, whereas we have a non-linear dependency on Q and V. Okay, so this fact that the dynamics of a multi-body system is linear with respect to U is going to be actually a key factor for the control methods we're going to develop. Okay, once we have written down the dynamics of the system, there are two main questions that we could ask ourselves to solve. One is the so-called forward dynamics problem. So the forward dynamics is when you are given Q, V, and tau, so positions, velocities, and torques, and you want to compute the accelerations P dot. So the forward dynamics is simply solved by inverting the mass matrix. And this is the problems that is solved internally by robot simulators. So every time you're using a robot simulator, what the simulator is computing inside is basically a solution to this problem, because you're providing the control inputs, tau, and the simulator is computing the evolution of the state through time, which goes through the computation of the accelerations of the system, v dot. We are mainly interested instead in the inverse dynamics problem, which is the one of computing the joint torques given the joint positions, velocities, and accelerations, because that's the problem that you need to solve when you're doing control. You typically know how you would like the system to move, so you know v dot, and instead you would like to know what is the command that you need to send to your actuator, so you want to know tau. So that's inverse dynamics. Okay, so that's everything I'm gonna say about modeling robot manipulators. Do you have any questions so far? Okay. So next subject is, what do we do if the robot manipulator makes contact with the environment? So it could be contact with a table, it could be contact with a human, or it could be also self-contact. Self-contact counts as contact. So if you have contacts, then the dynamics includes an extra term, which is this one highlighted in red. So this term is composed of multiplication of a matrix and a vector. So J is a matrix, which is called the contact Jacobian, and F is a vector containing the contact forces. So the vector of contact forces has a arbitrary dimension, and F, because it depends on which kind of contacts we are making. So if I'm making a so-called point contact, so let's suppose that I'm touching the wall with just the tip of my finger, that's a point contact. So in that case, the dimension of my force is going to be one. Is if the contact has no friction, it's one. If I can only push against the wall, it's one. But if the contact has a friction, it's three. Yeah, because I can push, but I can also apply lateral forces, either upwards or laterally. So I have a 3D force. If instead of having a point contact, I have a surface contact, so I touch the wall with my whole hand. In this case, what's the dimension of the force vector? Why 6? Yeah, because I have the same three-dimensional force as before, but now I can also apply a moment. I could make the wall rotate if I was strong enough. And it could rotate in all dimensions. So I can apply torques in all directions. So this is important when we are talking about legged robots, because if you have a biped where you have a foot which is maybe a rectangular foot, then that biped is going to apply a 6-dimensional force on the ground, because you have both the force and the moment. If you're using a quadruped, the feet are point-like, so they're very small. And when the quadruped touches the ground, it cannot apply any torque. It can apply only a force. So the size of the forces is going to be different depending on the geometry of your feet. And the size also of the Jacobian matrix is going to change depending on the size of the force F. So what is this Jacobian matrix? So the Jacobian matrix is, you can think of it, at least in as a first way of thinking about it, as the derivative of the contact point position with respect to the joint angles. So suppose that I'm touching the wall with the point of my fingertip. So the position of my fingertip can be expressed as a function of my joint angles. Because as I change my joint angles, my fingertip position is going to change. So this is the function C of Q. It's the function that computes the position of my contact point with respect to my joint angles. And if I take the derivative of this function with respect to Q, since I'm taking the derivative of a function that is multivalued, because my fingertip position is three-dimensional, so I have a three-dimensional function, which I'm deriving with respect to Q, which is an n-dimensional vector. This derivative is going to be a matrix. Okay. So in the same way as you take the derivative of a scalar multivariate function, you get a vector. If you take the derivative of a multivariate function with respect to a multivariate input, you get multivariate and multivariate, you get a matrix. So this matrix inside is going to contain all the derivatives. So we're going to have dc 0q with respect to q0. And then here we're going to have dc0q with respect to q1, etc. And here we're going to have dc m minus 1 q with respect to q0, and so on and so forth. So it contains the derivative of all the items of C with respect to all the elements of the vector Q. Okay, so all the combinations of the elements of C and the elements of Q give you a matrix. So the size of this matrix is going to be NF times NV, because the dimension of C is the same dimension of F, so it's NF. And the dimension of Q instead is NV. Okay. So this matrix is not going to be squared in general. It's going to be a rectangular matrix. Typically, it's going to be a fat matrix. So more columns and less rows. And here, however, you need to use it as a transpose. So it's going to become a skinny matrix. Okay, so basically this is how you take into account contact forces into the dynamics. You just map them to the joint space using the Jacobian transpose matrix. Again, computing this matrix is something we are not going to cover how we do it in this course. We're going to rely on a software, Pinocchio, for computing that based on a description of our robot model. Okay. And again, it's super fast to compute this matrix, so we don't need to worry too much about when we compute it, how we compute it. We just have a method, Jacobian, we call it. It returns this matrix. We have it. We can use it. Okay. Okay, so what I just described is valid for any kind of contact. Self-contact, contact with the environment, contact with a human. It's always like that. Now, let's focus on a special case of contact, which is the case of rigid contacts, which is very interesting for locomotion, because typically when you do locomotion, you do it on a rigid ground. So typically you need to work with rigid contacts. And rigid contacts have a peculiarity, which is that besides introducing contact forces, they also constrain the motion. Because once you make contact with a rigid environment, the contact point can no longer move in the direction of the environment. So if I touch the wall with my hand, then my hand can no longer move in the direction of the wall, because otherwise I would need to break the wall. But typically you're not strong enough to do that, so you just cannot move in that direction. And it's important that we take that constraint into account in our controller. So one way we could use to model that constraint is simply by using the C function, which I just introduced in the previous slide, which is the function that gives me the position of the contact points as a function of the joint angles Q. And I could say, well, my contact points cannot move anymore once I'm in contact. And so I can say C of Q equal to some constant value. Okay. That would be good. But actually, to make this constraint useful for us, we need to be able to express it as a function of the joint accelerations. The reason why will become more clear in the next slides, but just to give you an idea of why that's the case, it's the case because the joint angles is something that we cannot change instantaneously. So if the robot has a certain joint angle, that's it, we cannot change it. What we can change is instead the joint accelerations. So we need to make this constraint a function of the joint accelerations, which however is not difficult because we can just take the derivatives of this expression. So C of Q becomes C dot, we write it here, C dot of QV, and the constant in the right-hand side becomes 0, because well, a constant, if you take the derivative of a constant, you get 0. And C dot of QV can be rewritten as J times V. The reason why is quite simple. C dot is nothing more than the derivative of C with respect to time. And using the chain rule, we know that we can rewrite that as the derivative of C with respect to Q times the derivative of Q with respect to time. And that's simply J Q dot. So it's very simple to express C dot as a linear function of V. So this differentiated constraint represents the fact that the contact point velocities are null. And if we take the derivative another time, we get the derivative of a product is the first term times the derivative of the second term plus derivative of the first term times the second term. So we get J V dot plus J dot V. And 0 remains 0. Okay, so now we have a constraint which depends on the joint accelerations, which is what we wanted. By the way, it's also linear in the joint accelerations, which is going to be useful. And this constraint is basically saying that the contact point accelerations are null. So this is not exactly equivalent to saying that my contact points don't move, but it's almost equivalent. Why is it almost equivalent? Can anybody guess who has not taken my class before? So what's the difference between saying f of x equal to 5 and the derivative of f of x with respect to time is equal to 0? suppose that x is a function of time, of course. So the first one implies the second.
But the second does not imply the first one.
Why? What's the difference?
Because the derivative could be 0 even if the function is not 5.
But if
it has to be constant.
yeah, so the second one simply saying that that function remains constant, but it doesn't say at which value. But if we add the information that f of x of 0 is equal to 5, so that the initial value at time 0 of that function is 5, then we recover equivalence between the two. Make sense? So if we know that our contact points are where they are supposed to be at time 0, then imposing that the velocity is null is sufficient to be sure that they will remain always there. And to make this work with the second derivative, we need also to make sure that the velocity of the contact points at the beginning is 0. Because we are working on the second derivative, so the acceleration. So we impose the accelerations are 0, and we need to make sure that the position and the velocities at the beginning, when we start imposing the accelerations, are at the correct value, which is 0 for the velocities, and well, whatever for the contact points. So that's how we can use the constraints on the accelerations instead of those on the positions. So now that we have these constraints on the acceleration level, we can introduce them in the dynamics of the system. And by rewriting everything in matrix form, we get this expression. So we get an expression which is linear with respect to v dot, F, which are the contact forces, and tau, which are the joint torques. So this is linear with respect to these variables, but of course it's non-linear with respect to the state x, because both the mass matrix M, the contact Jacobian J, and also this vector here of bias forces H, and this term here, they all depend non-linearly on the state. But we still have a linear dependency on the control inputs, the contact forces, and the joint accelerations, which is not bad. Okay, so now we can try to solve the same two problems we discussed before. So the forward dynamics and inverse dynamics problem, but in the case where we also have contact forces and rigid contacts. So the forward dynamics problem, remember, given Q, V, and tau, we want to compute V dot, and actually this time we add to V dot also the contact forces, because those are unknown. And we can quite simply do that by solving this linear system of equations. So I've just taken the expression in the previous slide, and I moved tau to the right-hand side because now tau is known. And I solve for V dot and F. And this matrix here that I get is square. So hopefully it can be invertible. It might not be invertible depending on J. So M, the mass matrix, is always invertible. So if J is a full rank matrix, then also this is going to be invertible. If J is not, then this is not invertible. And that is related to the geometry of my contacts. But yeah, we don't need to go there. It becomes a bit complicated. and instead the inverse dynamics problem, so the one solved by the controller. So given the specification on the motion, so positions, velocity, and accelerations, we want to compute the joint torques and the contact forces, because the contact forces are always unknown. And in this case, if we try to solve the previous system of equations, what we get is this, that we can compute tau and f using this expression, where we cannot take an inverse here in general, because in general, this matrix is not square. It can be whatever dimension, it depends on the dimension of J. And so in general here, we need to work with a pseudo-inverse. And here we need to take the implicit assumption that the V dots that we are given as a target must satisfy the constraints on the rigid contact. So JV dot must be equal to minus J dot V. But that's reasonable. I mean, if you are given a motion to track, we expect this motion to be consistent with the geometry of the task we are trying to achieve. Okay. Yeah, we can think of this as a primitive version of inverse dynamics control with rigid contact, which is instead what we're going to develop in its most advanced version in the next few hours. So this is like a very basic way of doing inverse dynamics control when we have rigid contacts. If you have a reference motion, V dots that you want to follow, you can just compute the corresponding joint torques in this way. Okay, so the next topic would be modeling length robots, but I think I would take a break right now because it's quite boring, this lesson, and it becomes more interesting later. So I don't want to make you sleep too soon. So let's take 10 minutes. I'll see you back here at 3:20. Let's start again. So we have seen how we can model robot manipulators and how this model can be extended when we have contacts, more importantly, rigid contacts with environments, which are predominant in legged robots. But let's now see how we extend the model of a robot manipulator into the model of a legged robot. So the main issue with legged robots is that they are not attached to the ground. They can move around. So just knowing the relative angle of each joint is not enough to know where the robot is in space, because the robot can maintain a fixed configuration like this one that you can see in the slide. But if you move the robot around, the robot has changed configuration. But this is not reflected by looking at the joint angles. So we need to augment the state of the system to contain some extra information that allow us to know where the robot is located in the environment. So the solution that has been adopted is the one to extend the robot configuration with a vector representing the position and the orientation of one of the rigid bodies of the robot. So this one special rigid body is called the base frame, the base body, or just the base. And this extra information is going to be called XB. That's the pose of the base. Whereas the vector of joint angles, we're going to call it QJ. So putting these two together, we recover the whole configuration vector Q. So now let's dig a bit deeper into what's inside this XB. So this XB needs to represent both the position and the orientation of one of the rigid bodies of the robot. So to represent the configuration of a rigid body, we need an element of the SE3 space, the special Euclidean group. So we can think of it as a combination of a translation and a rotation. Translations are easy because they are just living in a Euclidean space. So they're just elements of R3. You have just three scalar values, period. And that represents the position of this body. The tricky part to work with is the orientation, because there we have different ways to represent it. So rotations are in general elements of SO3, which is a special orthogonal group. And they can be represented in different ways. You have the so-called minimal representations, which use only three values. Examples of these are the roll PTO angles, or the Euler angles, which are just a generalization of roll PTO. And you have the redundant representations, which are the ones using at least 4 elements. So examples of these are quaternions or rotation matrices, which probably are the most well-known ones, the 3x3 matrices that define a rotation. So we might be tempted to use the minimal representations because they're very intuitive to work with and you only have 3 values. But the problem is that when you use minimal representations, you have singularities. So if you have taken any class on robotics, you should be familiar with the concept of singularity. In practice, singularities arise from the fact that with these minimal representations, you don't have a one-to-one mapping from the possible orientations and the representations corresponding to them. So there are orientations that can be represented in multiple ways using that convention for the representation, which might not seem like a big issue when you just discuss about it. But in practice, when you're using this with numerical software, they tend to make the numerical algorithms work very poorly in practice. So people have steered away from minimal representations and have moved to the redundant representations. In particular, quaternions are a very good trade-off because they only use 4 values. So you have just 1 extra elements, but you get rid completely of the singularities. So you don't have any numerical issue when working with them. You could also work with rotation matrices, but then you need to store 9 elements so that they are very redundant. So what we're going to do is that we are going to represent the XB vector, so the one representing the pose of one body of the robot, of the base, as a 7-dimensional vector. The first 3 elements are going to represent the position of this body, and the last 4 elements are going to represent the orientation under the form of a quaternion. Okay. So let me briefly introduce how the quaternions work. Not that we really need it for this class, but since we're going to use them, I think it's nice if you have at least a rough idea of what's inside them. Okay, so quaternions work in this way. You probably already know that any rotation in 3D can be represented as a rotation around a fixed axis by a certain angle. So no matter what kind of rotation you want to apply, you take an object in a given orientation, you just take another orientation, doing how many movements you want. The rotation from the starting orientation to the target orientation can be always obtained by rotating around a single fixed axis. This is just a fact. So imagine this axis, we call it U, and the angle of rotation, we call it theta. Then the corresponding quaternion would be this 4-dimensional vector, where C and S are the sine and the cosine of theta over 2, and ux, uy, and uz are the 3 elements of the rotation axis. Okay. So it's quite straightforward to see that from the information you have here, you're able to recover both u and theta. Okay. And well, once you have u and theta, you have all the information you need for representing the orientation. So this quaternion contains all the information to represent the orientation. And quaternions are always normalized. So if you compute the norm of this vector, you always obtain 1. So they are a 4-dimensional vector, but they are subject to a 1-dimensional constraint, which is this, which kind of makes sense if you think about it, because you have 4-dimensional vector minus 1 constraint. So you get 3 degrees of freedom, which are the ones of the space that you want to represent, which is the space of possible orientation. Okay. So now a robot configuration Q contains the base, position and orientation, XB, and the joint angles QJ. XB is composed by the base position, PB, and the base orientation, OB, which belongs to R7. However, the robot velocity doesn't live in the same space because the velocities of the base are going to be represented by a 6-dimensional vector, because the angular velocity is a three-dimensional vector, doesn't have 4 dimensions, has the quaternion. Okay, so one of the key challenges of working with these redundant representations for the orientation is that right now the configuration vector and the velocity vector, they don't have the same size anymore. So the configuration vector is 1 element longer than the velocity vector. That was not the case with robot manipulators. Okay, so it takes a little bit of mental effort to adapt to this, especially when you're coding. So like if you want to do an integration in time, before you could do just the next value of q, so qi plus 1 is equal qi plus delta t times q dot I. That you could do it to do a forward integration in time. And now you can no longer do that because q and q dot have different sizes. Indeed, that's why we don't call them q and q dot, but we call them q and v. Because q dot is misleading. It makes you think that it's a time derivative of q, but it's no longer the time derivative of q. It's almost the time derivative of q, except for the orientation, because here we have the angular velocity, but the angular velocity is not the rate of change of the orientation. So omega b is not the derivative with respect to time of OB. Okay. Also, they don't have the same dimension. Of course, you could compute the rate of change of OB. And if you computed that, there are then expressions for mapping the rate of change of OB to omega b. So there is a direct mapping from O dot to omega. But we actually don't need to do that because the library that we are using for multi-body dynamics modeling takes care of everything for us. So every time we need to do an operation such as an integration, we just have a method which performs the integration using the appropriate conversion between quaternion and angular velocity and vice versa. But you just need to be aware of this problem so that you don't make mistakes when you're coding. So here we can see that there is a direct relationship between the angular velocity and the rate of change of the rotation matrix, R. So this R would be the 3x3 rotation matrix, which you should be already familiar with because that's the most common way of representing rotations. And we can see that this is the relationship between omega, so the angular velocity, and the rate of change of R. So this omega hat represents the skew-symmetric matrix associated to omega. The skew-symmetric matrix is a matrix such that the transpose is equal to minus the original matrix. So let me write it. Omega b hat transpose must be equal to minus omega b hat. And the only way you get that property is if you have a matrix which has zeros on the diagonal and something like that. In the off diagonal terms. The minus and plus could be wrong because I don't remember it by heart very well. But Wikipedia is good for that. if you look for skew-symmetric matrix, you find how it is computed exactly, but it's a matrix that looks like that. So you can use this matrix, this expression here. It's basically a linear dynamical system. If you look carefully, your state here would be R. So we have the derivative of the state on the left-hand side equal to a linear function of R on the right-hand side. So this is exactly a linear dynamical system. You're typically used to seeing this in the form x dot equal ax, but this is exactly the same. It's just that in this case, x is a matrix and not a vector. But apart from that, it's the same as usual, which means that you know the solution for a linear dynamical system, which would be x of t equal e to the ta x of 0. And here is just the same where I replaced x with r. So this is the expression that you need for integrating an angular velocity and getting the corresponding rotation matrix. In our code, we are not using the rotation matrix, we are using the quaternions. There are similar expressions for the quaternions, they're just a bit more convoluted. So I prefer to show you here the expressions for the rotation matrix. Also, maybe you have already encountered these expressions, so they may look a bit more familiar to you. Have any question on that part? Okay. Well, Q and V have different sizes. So NQ, which is the size of Q, is going to be NV plus 1 because of this extra element in the quaternion. So this actually, we are discussing this for the subject of legged robots, but this applies to all mobile robots. So what I'm saying, if you're working with a drone, underwater robot, even just a mobile robot with wheels, you have the same thing going on. It's just that people working with mobile robots typically are lazy, since they use a 2D representation. You do x, y, theta, where theta is the angle. So that would correspond to a minimal representation for the joint angle, for the orientation, which is not very good. And it exists also the quaternion for the 2D case, which is simply the sine and the cosine of the theta angle. So in 2D, the quaternion would be a two-dimensional vector, which has always size norm equal to 1. So if you want to do things properly, even with a bidimensional wheeled robot, you should use these kind of tools. Okay, then underactuated systems. Well, I already told you that these are systems for which the number of actuators is less than the number of degrees of freedom. And when we have an underactuated system, such as every mobile robot, what we can do is that we can order the degrees of freedom inside Q, so that we have first all the unactuated degrees of freedom, and then all the actuated degrees of freedom. And we can label them QU and QA. We can do the same thing for the velocity. So we have VU and VA. And then we can introduce a selection matrix, which we are going to call S. It's a very simple matrix which contains only zeros and the identity matrix inside. And this is the matrix that, given the vector of the robot velocities, V, it selects the actuated part, VA. The reason why we need this matrix is to model the dynamics. So we're going to see it in a moment. So just to clarify the obvious, for a legged robot, the underactuated part would be the base pose, the one we have introduced, which wasn't there before, that is not actuated because you don't have a propeller. I don't tell you where to make you fly. So the dynamics of an underactuated mechanical system, which is just a fancy way of saying a legged robot, is basically the same as before, but now we have this S transpose matrix here. So the selection matrix, which has the job basically of extending the vector of torques, adding a bunch of zeros on top. So if we write S transpose tau more explicitly, what we get is a vector containing 6 zeros on the top and the vector tau in the bottom part. And if we decompose this expression into two expressions, one for the underactuated part and one for the actuated part, we get these two equalities here. So this is for the unactuated parts. And indeed, you can see that it doesn't contain the vector tau. There is no actuators. And the bottom part instead contains directly the vector tau. So in this way, we can clearly see the underactuation. There are the first 6 rows of the equation that do not depend on tau. They only depend on the contact forces F. So this kind of gives you the intuition that in order to control the underactuated part of the robot, which is basically the position of the base of the robot, you need to control the contact forces. But you cannot directly control the contact forces. You need to control the contact forces through your control inputs, which are the joint torques. So we will need to figure out how to compute tau so that F assumes a certain value, which allows us to control the underactuated part of the system. Okay, so this is just a recap of everything we have seen so far. We can see here the dynamics of a robot manipulator. That's the simplest form. Then once we have contact, we extend this dynamics with the J transpose F term, which accounts for the contact forces. And once we move to a legged robot, which is underactuated, we need to account for underactuation by adding this S transpose matrix, which adds all the zeros in the top part of the equation, which is the passive part of the equation. And if the contacts are rigid, we have to take into account the rigid contact constraints expressed at the acceleration level, which is this JV dot equal minus J dot V. So basically everything you need to remember from this lesson is in this slide. And I think that was the last one. Any question before we move to the next pack?
Yeah, maybe just like curiosity. I was like, I've used, I had the chance to use both quaternions and rotation matrices to represent the orientation. I was wondering, if, there are advantages to using a rotation matrix because you have to carry all the extra terms with respect to quaternion. So you make that faster to compute, maybe. So the algebra is easier.
So there are people that are very passionate about these subjects. I'm not one of them. That was a very honest answer, by the way. I know that there are situations in which quaternions are more are faster, and situations in which rotation matrices are faster. I think that if you need to apply a rotation to a given vector, the rotation matrix is the fastest, because you have just to do a matrix vector multiplication, whereas for the quaternion, the expression is a bit more convoluted, so it takes some nanoseconds more. And so there is a threshold that if you need to rotate a certain number of vectors and you have a quaternion, if the number of vectors is sufficiently large, it's better to convert the quaternion into a rotation matrix and then just apply the rotation matrix. But if the number of this vector is sufficiently small, it's better directly to apply the quaternion. And people go nuts with this stuff and they write papers about it. Mm-hmm. To me, it's not super interesting. As long as I have a fast library that allows me to compute the quantities I care about, then how these quantities are represented inside that library, I don't care. In the end, if I need to visualize a rotation, I need either a 3D viewer that shows me that rigid body in that orientation so I can see it, or I need to convert the quaternion or rotation matrix in Euler angles and then do these 3 plots, because that's the only thing I can understand as a human being. And I share that feature with most human beings. I've never heard of anybody who plots the rotation matrix or the quaternion. So yeah, that's my very honest answer. I don't know if you enjoy plotting rotation matrix, let me know. I will update my knowledge.
They are used a lot for quadruped control. At least I've seen them in a lot of paper rotation matrices. So I was wondering if there were some these particular reasons for that, some upsides to what they're doing. So
I mean, for doing the math, yeah, people tend to use the rotation matrix much more than the quaternion, because I think it's simpler. But for computation, it's a bit annoying to carry around all these extra values. And so people tend to use more the quaternion for computational implementation. That's my just very high level knowledge of the subject. You're welcome. Okay. I think I'm in the wrong page. Okay, so enough with the modeling. Let's start talking about doing control. And let's start with the simplest form of control, which is in joint space. So let's assume we are given a robot manipulator, which has this dynamics. We assume that the robot is not making contact with the environment, so the dynamics is in its simplest form. We have a reference joint trajectory, QR. So we know exactly what kind of movements the robot should do. And we want to find the joint torques, so the motor commands, so that the robot follows that trajectory. How can we do it? Well, that's actually quite simple. If we assume that we know the dynamics of the system, so we can compute M and H, and we can measure the state, so we can measure Q and V at every iteration of our control loop, then the solution could be simply to set tau equal to M times v dot desired plus h. So this is exactly the same expression we have there, but instead of using v dot, we use a value v dot desired, which represents the desired accelerations that we would like to see on the joints. So of course, if you substitute these expressions there, it is trivial to see that the result is that v dot is going to be equal to v dot desired, because h cancel with h, and the mass matrix M is always invertible because it's a positive definite matrix. So you can also multiply both sides times M inverse, and you get simply v dot equal v dot desired. And now we just need to select v dot desired so that Q follows Qref. But this is a linear system regulation problem, so it's very simple. We have a direct control over the acceleration of our system, so making it converge to a reference trajectory can be done with a very simple proportional derivative controller. You might be tempted to set v dot desire simply equal to v dot reference. So v dot reference would be the time derivative of q dot reference. So you would have let's start with vr of t would simply be the time derivative of qr of t, and v dot r of t would simply be the time derivative of vrt. So you could simply say I'm going to set my v dot reference equal to my v dot desired, but that's not going to work well, because just imposing the acceleration, as we have seen before, is not enough to guarantee that the position constraint is satisfied. You need to have the initial conditions that are matching, and you also need to have zero errors everywhere. So zero errors in your state measurement, zero errors in your model knowledge, zero errors in your computation, zero errors in your actuators. So that's not very realistic. So what works much better is to add a proportional derivative feedback term to this feed-forward acceleration, v dot r, that stabilizes the system around the reference trajectory, so that this reference trajectory becomes an attractor and the system tends to go towards it even if it is disturbed. And the disturbances could be physical disturbances, or it could be just modeling errors, state measurement errors, and so on and so forth. So here, of course, you will need to tune these two gain matrices, Kp and Kd. Typically, you would take them as diagonal matrices, and they always need to be positive definite. Otherwise, you are not stabilizing. You are destabilizing. It's not exactly desirable. So tuning these two it's an art, but not a very difficult one. Try Kp equal to 10, and then increase Kd at need, depending on how much friction you have on your system. Okay, we can actually also see that under these conditions, Q converges to QR. It's very simple. So the closed loop dynamics that we have is the following one. We can define the difference between Q and QR as the error E. So the difference between V and VR becomes E dot. If we move VR to this side, then we also get E double dot on the left-hand side. So we get E double dot equal minus KD E dot minus KPE. We can write this as a linear dynamical system by introducing this augmented vector X that contains both E and E dot. And once this is in the linear dynamical system format, then we know how to analyze the stability of the system by simply computing the eigenvalues of this matrix A. We know if the eigenvalues have a negative real part, then the system is stable. So we get convergence to 0. And since the state contains both E and E dot, it means that the error goes to 0. And this happens anytime we have a positive definite matrices for the gains AP and KG. Actually, this proves more than convergence. This proves even stability, which is something even nicer than convergence. It doesn't mean not only we get there, but if we start close, this ensures that we remain close. So if your reference trajectory starts where your robot is at the beginning, you will always remain close to the reference trajectory. That's basically stability. Okay, so the control law that we get by putting everything we have said so far together is the following one. And this is known under different names. I typically call it inverse dynamics control. And I think these days most people use this name. But in old robotics textbooks, this was known as computed torque. And if you talk to people that come from control theory, such as Luca, he will refer to this as feedback linearization. So this is just vocabulary, not adding any new information. Actually, feedback linearization is a more general class of control techniques, where this is just an example of feedback linearization. There is another variant of this control law where you just move the two feedback terms outside of the parentheses, and you get this expression here. This is a bit trickier to prove that it is stable and convergent, but it can be done. And in practice, this can work even better than the one above, even though it's less trivial to analyze. There are also other even simpler control laws for robot manipulator, which I'm just mentioning here for your information. One very common is PD plus gravity compensation. I think for robot manipulators, this is probably one of the most popular, if not the most popular. So you're just compensating for gravity, which is doing most of the job on a robot manipulator. And then you're controlling everything else with a proportional derivative term. So with respect to the previous one, you're not compensating for Coriolis centrifugal forces, and you're not accounting for the mass matrix. And if you have an industrial manipulator with high gear ratios, typically this works very well. And if you're super lazy, you don't even want to compute the gravity compensation, you can replace gravity compensation with just an integral error term, which is going to act as a gravity compensation, just slower to converge to the correct value. But if your robot moves slowly, then you don't care. And this works as well as the gravity compensation. Yeah, both these control laws are stable and ensure convergence to the target joint angles. So in theory, the inverse dynamics control, which I showed you first, should be a better version of the gravity compensation plus PD, which should be a better version of the PID, That's what the theory and the intuition also would suggest. In practice, however, that's not always the case. And I've seen that the opposite can occur, because the more advanced control laws, such as inverse dynamics control, rely more on a model. And if your model is not good, then actually it would be better not to rely on the model at all. And so you could get a better performance from the simplest PID controller than from the more advanced inverse dynamics controller. So beware of that. That's especially true when you have the high frictions I was mentioning before, because those are very difficult to compensate and they make your model very wrong. Okay, so now we have seen inverse dynamics control in its classic form, which is how it has been introduced probably in the 70s or even the 60s. But more recently, there has been a trend of seeing control algorithms as special instances of optimization problems. And that's kind of the mindset I would like to communicate to you in this course. So let's take the inverse dynamics controller, which we have just seen, and let's try to see how it can be cast as the solution of an optimization problem. And then we'll see how that enables us to add extra bits inside the problem to make the controller more expressive and more powerful. So let's take this optimization problem. The decision variables of the problem are the joint torques and the joint accelerations. The constraints of the problem are simply the dynamics of the robots. And the cost function is simply the squared difference between the desired acceleration and the acceleration that I have as a decision variable. So what this problem is doing is trying to find the joint torques and the joint accelerations that satisfy the dynamics of the system, while also achieving a joint acceleration that is as close as possible to my desired accelerations. So this, I think, makes a lot of intuitive sense, because that's exactly what we are trying to do. And this problem has also a trivial solution, because for sure, the value of V dot that minimizes the cost is V dot equal V dot desired, because we get a zero cost, which is the minimum since it's a squared function. And once we have V dot equal V dot desired, the solution for the constraint is simply setting tau equal to m times V dot desired plus h. So problem trivially solved. And this is exactly the solution that we have seen before as the inverse dynamics controller. So we can see that basically solving this optimization problem is equivalent to using the inverse dynamics controller from a few slides ago. Good. There is no advantage so far, but that's a fact that we can acknowledge. So this kind of problem here is called a least squares program, because it has linear constraints, and the cost function is the 2 squared norm of an affine function. So it comes under the form norm of ax minus b squared. That's just a special case of that form. Why it's important to know that it's a least square program? Well, because least square programs can be solved super fast. So we know that if you're able to formulate our problem under this form, then we are not afraid of solving it inside a control loop, because it's fast. So actually, this gives you the detail of least square programs. They can have linear inequality constraints, linear equality constraints. The cost function is the 2 norm of a linear, which if you compute, you get this expression here. So you can see that it's actually a quadratic function because you have this term here, x transpose ax, which is a quadratic term. And the second one is a linear term. And the third one is just a constant. So it's a quadratic. And it's actually a convex quadratic because the Hessian of this quadratic is always positive definite. So A transpose A, it's always a positive definite, a semi-positive definite matrix. Indeed, least square programs are a subclass of convex quadratic programs, which have the same constraints, but allow for a more generic cost function, which is the quadratic cost function. So the least squares cost is just a special case of a convex quadratic cost. So we will see that we can solve this kind of problem quite easily at 1 kilohertz. So in less than 1 millisecond, we can solve one of these problems for the size that we are interested in. Of course, if you add 10,000 variables, no, you cannot solve it in 1 millisecond. But if you have something like 50 variables, which is typically the range we're going to work with, then we can solve it in 1 millisecond. Okay, so let's start from the problem formulation we have seen, this one, which is equivalent to the classic inverse dynamics control. And let's see how we can make this a bit more interesting. So one thing I would like my controller to be aware of is that my actuators don't have infinite torque. They have a limited amount of torque that they can generate. And this can be very easily taken into account if I'm adding to the problem a couple of inequality constraints to say that my torques tau should be bounded between tau min and tau max. So this is allowed under the least square program format because these inequality constraints are linear. And so I can simply add them and my solver is going to be able to take them into account. Another thing I could take into account very easily is my motor current limit. So if I'm using an electric motor, which most robots do these days, my motor current is going to be proportional to my motor torque. And this constant here, you can typically find it in the motor datasheet. So you know how to compute the current from the torque. And so you can use this relationship to add also current limitations inside your least square program by expressing the current as a linear function of the joint torque. So this current limitation could come also from the electronics, not only from the motors. Maybe your motor can accommodate a current of 10 ampere, but your electronics can only allow for 9 ampere. So you want to limit the current to 9 for that reason. Another thing that is very useful to account for in practice are the joint velocity limits. So either your motor or your gearboxes could have a limited velocity that's provided by the manufacturer, who tells you don't exceed this velocity, otherwise I'm not going to guarantee that this piece of hardware works. So you want to try to stay within the velocity limits. The joint velocities, however, are not part of the decision variables of my problem because I only have the joint torques and the joint accelerations. So I need somehow to express my joint velocities as a function of my decision variables to include these constraints. This actually is quite easy to do because I can simply put the constraint on the joint velocities in the future. So at time t plus delta t, where t is the current time and delta t is the period of my control loop. So I can impose the constraint on the joint velocities that I will have at the next control loop, because I can express my next joint velocities with this approximated computation. So this is a so-called Euler integration scheme, where I assume that my acceleration remains constant for the whole time step. But this approximation is very reasonable in practice because delta t is typically between 1 and 10 milliseconds, so it's super small. So by doing that, I have a function of my accelerations v dot, and then I can add constraints on this function. So my final least square program is going to look like this. Besides having the dynamics as a constraint, I also have inequalities for the torque limits, for the current limits, and for the joint velocity limits. And all of this doesn't change the form of the problem, which is always a least square program. Okay, so this means that I can solve this optimization problem within 1 millisecond quite easily. Okay. But now I have something that is much more advanced than the initial starting point, because now my controller is going to take all this limitation into account when trying to find the joint accelerations that are as close as possible to the desired value. So this is something that if you had to design an algorithm by hand to figure out what are the joint torques that minimize this, trust me, it wouldn't be easy. It wouldn't be easy. But using numerical optimization, you can solve this problem very easily. Now, the burden on you is not solving the problem. That is the job of the solver. The burden on you is modeling all the quantities that go inside this problem. So that's what we're going to focus on during the implementation. There is an extra constraint that we could add, which is the one on the joint positions. I've left this as a last one because this is actually quite tricky. So we might be tempted to do the same trick that we used for the joint velocities. That is, instead of applying the constraint on the current joint positions, we apply it on the joint positions at the next iteration. So q of t plus delta t. And if I assume that I have a constant acceleration for the time step, the expression that I get is this one, which is linear with respect to v dot. So I could add this as a constraint inside my problem. The issue is that this is not going to work very well in practice. And the reason why it doesn't work very well in practice is because this is what's going to do is that it's going to allow you to get very close to your joint position limits. And then when you're very close to it, you're just about to hit the limit, it's going to ask you to decelerate super fast. So this works if you have an infinite acceleration capability, which you don't in practice. And so this is going to lead you to an optimization problem, which is unfeasible, because this constraint is going to ask you to decelerate super fast, but then you have the limit on the joint torque, which prevent you from applying a joint torque which is too large. And these two constraints are going to be incompatible, and your solver is going to tell you this problem is unfeasible, sorry. And you're going to be left without anything to do at that point. So the reason is that this constraint is not looking enough into the future to be able to anticipate the problem of the joint position limits. And there are approaches that allow you to do this anticipatory behavior in advance, and include that inside this kind of least squares based optimization controller. But that would take me a little bit to explain to you how that works. So I just remind you to these publications in case you want to know more about how that is done. And yeah, one of them is probably mine, and the other two are state of the art. I think the best one is mine, of course, but I have a bias in that. I've been punished for my arrogance. Okay, so to summarize what we've seen so far, inverse dynamics control, which was our starting point, is this. There is a second version of the same where you just remove the parentheses and still works. It's provable that this is convergence and stable. You have simplest control methods such as PD plus gravity compensation. It's very common on robot manipulators, or even PID. It's very common. But we can also formulate the inverse dynamics controller as a least squares optimization problem under that form. And the main advantage of doing that is that we can then add inequality constraints to the problem, such as torque limits or current limits or joint velocity limits, or that's it. I didn't add the joint position limits because I didn't explain you how to do that properly. And these are the papers on the joint velocity, on the joint position limits, in case you want to take a look at them. And that's it. Okay, I think we could do another short break just to breathe some fresh air, and then we do another half an hour before we finish today. Okay, let's move on and let's go from joint space control, which is what we have seen in the previous hour, to task space control, which is a generalization of joint space that allow you to do more advanced control. So when you work with a joint space controller, everything is nice and simple, but the issue is that you need a reference joint space trajectory. So you need somehow to have pre-computed exactly what is the motion that you would like to see for your robot in joint space. And typically in most applications, you don't know that. If you think about even the specific applications we are targeting in the end of this course, which is walking, think about the motion of a walking robot, you kind of know how the feet should move of the robot, but it's very difficult for you to figure out how the joints should move. And that's actually the case in most practical cases. So it is much more natural to express the desired movement of a robot in terms of the behavior of some key points of the system rather than with respect to the behavior of each joint. So task space control allows us basically to do that, to start from a reference movement for the end effector, for instance, whereas actually end effector could be anything. It could be, well, the hand, but it could also be a foot of the robot. It could be the head of the robot. It could be the center of mass of the robot. Whatever function of the robot state could be the end effector. And given a reference trajectory for that end effector, we want to figure out how to control the system so that it follows that trajectory at its best. So one option, a very simple one, could be to try to map the desired reference trajectory for the end effector to a desired reference trajectory in the joint space. Do this computation offline, maybe when we have plenty of time to do computation, and then apply a joint space controller. That would probably be the simplest option given what we have seen so far, so that we can reuse the joint space controller. And this could kind of work. We would need to solve this optimization problem. Well, they're actually constraint satisfaction problems because we are not minimizing anything. We are just trying to find the joint angles so that the forward geometry of the given joint angles gives us the desired reference position for the end effector. So the forward geometry Fg is a function that computes the position of an end effector starting from the angles of the joints. The problem is that, well, we will need to solve a bunch of these problems offline, which is a bit annoying, that these are nonlinear optimization problems. So they can be non-convex and quite difficult to solve, but we could do it. Wouldn't be the end of the world. It becomes very difficult to do it if you cannot do it offline. So if you have to solve those problems online while you're controlling the robot, there it becomes an issue because there you have very little time. And in many practical scenarios, you need to do it online. Why do you need to do it online? Because maybe you don't know the reference trajectory beforehand. So imagine if your robot needs to follow a certain target, you don't know where the target is going to go. So you cannot know in advance what is your reference motion. So you just discover the reference target online. And so you will need to do this computation online, and that's a challenge. So in those scenarios, it becomes much, much easier to work with a controller that works directly in task space so that you don't need to do any pre-computation. Also, there is another thing that tracking this reference joint configuration QR would be sufficient to tracking the reference task configuration, but it's not necessary, because in general you have infinitely many possible joint configurations that correspond to the same task configuration. Like for instance, my hand, it can be in this position, but my arm can move. If I pre-compute a reference joint configuration and I track that, I lose this extra freedom, which I could use to reject perturbation or to minimize the energy consumption and so on and so forth. So I'm also losing something in terms of the control freedom. So the option number 2, which is the best one and the one that I'm going to explain to you, is doing directly control in end effector space. So going from joint space to end effector space control is quite simple. Basically, we move the PD controller to joint space, where we have this weird variable v, which represents the acceleration in end effector space. We have the usual derivative term, which multiplies the velocity error, and the position term, which multiplies the position error. And we write down the relationship between the joint space configuration and the end effector configuration, which is given by this forward geometry function, fg. We take the derivative of this function with respect to time. And what we get is actually very similar to what we have already seen when we differentiated the contact constraints. So we get x dot equal jv, okay, where j in this case is the derivative of the forward geometry function with respect to the joint angle. So it's a matrix, a rectangular matrix typically, as it was for the contact Jacobian. It's always a Jacobian, just of a different function. And well, here I don't know why I added some other notation, but the content is always the same. We take another derivative, so we get accelerations equal jv dot plus j dot v. Yeah, I see what I did. I replaced that weird v with this more familiar x double dot, which just simplifies a bit the notation, so it's more clear that that's an acceleration. Okay, so after we have these expressions that relate the acceleration of the end effector with acceleration of the joints, we could compute the joint accelerations that result in the desired end effector acceleration by simply inverting this linear equation. So since this is a linear system of equations which is not square, it may allow for either infinitely many solutions or no solutions at all, depending on the size of the matrix J and its rank. In general, what happens in this context is that we have infinitely many solutions because J is a fat matrix. And so we have infinitely many solutions, and we can compute the minimum norm solution by using the pseudo-inverse of the Jacobian. So we just do J pseudo-inverse times x double dot desired, so the desired and effector acceleration minus J dot V. Okay, so we have a linear system of equation, and we just compute one solution of this system. Once we have the desired acceleration, we can just plug it inside the system dynamics to compute the corresponding torques. And that would be the analytical way of deriving an end effector space control. However, you probably have already got the mindset of this class. We don't want to do things analytically. We want to cast problems as numerical optimization and then use a solver to find the solution. So how do we do this inside a least square program? Well, it's actually very simple. Okay, this is just a summary of what we have already seen with lots of discussion, which I've already covered. So this is a summary of the end-effector control law, which we have just derived. So we compute the desired acceleration in end-effector space. We map from end-effector space to joint space using the Jacobian pseudo-inverse. And then we map from joint accelerations to joint torques using the inverse dynamics. So what we can do is to cast an optimization problem, which has the same variables as before, so tau and v dot, the same constraints as before, which are the system dynamics. And as a cost function, instead of measuring the error between the joint accelerations and the desired joint accelerations, we measure the error between the end-effector acceleration and the desired end-effector acceleration. So it's actually just one line of difference switching from v dot to x double dot. Okay. X dot is not a variable of the problem, so I cannot write directly x dot, but I know that x dot is j q double dot or jv dot plus j dot v. It's a linear function of my joint accelerations because I've derived this expression a few slides ago. So I express the end-effector acceleration as a function of the joint accelerations. Okay. And if you take a look at it, you can see that the cost function, it's still a least square cost because we have the 2 norm of a linear function of v dot. So this is the linear part, and this is the constant part. So the only extra computation that we need is that we need to compute the Jacobian. But again, Jacobians are not an issue. We have a library that computes them. And we need to compute this term here, j dot v, which again can be easily computed using this library. Actually, we are not computing j dot and then multiplying it times v, but we have a method to compute directly the product j dot times v, which is way faster than computing j dot and then multiplying it times v. Okay. So once more, what's the advantage of casting this problem as an optimization? We can add inequality constraints on top. So now all the inequality constraints that we had introduced when discussing joint space control, we can also include them here. Okay, this was just a zoom in on the fact that since the linear system that we are solving typically has a fat matrix A, when we are solving it, we have infinitely many solutions in general. And the solution that we compute using the pseudo-inverse is the minimum norm solution. So is the one that minimizes the squared norm of the variable x subject to satisfying exactly or satisfying in the least square sense the linear system of equations. Okay, so among all the possible solutions of this system of equation, we take the one that minimizes this norm. That's what we get for free basically when we do the pseudo-inverse. We're actually not going to do the pseudo-inverse. We are simply going to cast the optimization problem, and then the solver is going to figure out what to do with that. But quite likely the solver is going to return you the minimum norm solution if you do it in this way. Depends a bit on what algorithm the solver implements, but as far as I know, it's most likely going to be the minimum norm solution. Okay. The concept of end effector, we are used to thinking about it in robotics as just the terminal link of a robotic arm, but it can be anything. So when people talk about generalized end effector control, typically they refer to it as task space control, because task is this more general concept of whatever function of the robot. It can be also called a control objective. And we can make this a bit more formal to see how general it is and what are the subtleties we need to take care of when we generalize this. So let's describe a task as a function, which we're going to call E for error, which we want to minimize. So this is very similar to what people do in optimal control. So if you're familiar with optimal control, this should sound very natural. So this function E measures the error between a real and a reference output of the system. This output, we're going to call it Y. And Y can be any differentiable function of the state or the control. So of course, joint space control and effector control are special cases of this more general framework of task space control. You just need to set Y equal either to the joint angles or to the end effector configuration. So the error is the difference between Y and Y star, where Y star is your reference trajectory for these outputs that you want to track. Yeah, note that this is a bit different from what people do in optimal control, because here the error depends only on the current value of the state and the control, whereas in optimal control, typically the function that you're minimizing depends on the whole trajectory of state and control input. So it's similar to optimal control, but it's not the same thing. So don't get confused by this similarity. There are still different approaches related, and we can talk about it later if you want, but they are distinct. So the idea is that given this error function that measures how close we are to achieving what we want to find an affine function of the decision variables of my problem, which are the joint accelerations v dot and the joint torques tau, which I can put as a cost function of my least square program. That is my objective. So we're going to see that we can work with three different kinds of functions. We can work with functions of the control U, function of the robot velocities V, or functions of the robot configuration Q. We could also have mixes of these, but in practice, that very rarely happens. You typically have functions of either one or the other. So we're going to deal with these three cases separately to make things a bit simpler. And let's just analyze the first case, which is the simplest. In case our error function depends on the control input U, it must be an affine function of U, because U is already a decision variable of my problem. So if I want to put this inside the cost, and my cost needs to be a least square cost, what I put inside the 2 squared norm must be affine. So if my error function depends on U, it must depend on U linearly. We cannot have a nonlinear dependency on U. So that's the simplest case. For the other two cases, instead, we can have a nonlinear dependency. And the reason why will become clear in a moment. So the problem is that Q and V are not directly decision variables of my problem. So I cannot directly take this error E and use it as a cost inside my least square program, because this cost would not depend on the decision variables. So I need to find some other function that I can minimize and which leads this error towards zero. So what kind of functions could I try to minimize? Well, instead of working directly on these errors here, E, I could work on their time derivatives, which is a trick we have already used. If you think about it, when we developed the contact constraints, we took derivatives to express constraints from position to acceleration level. Here we can do the same. We have this cost expressed at the position level. We need something at the acceleration level to use it as a cost function. So we take the derivatives. Okay. And we need then to impose a certain value for the derivative of these functions so that the error function tends towards zero, which is what we want in the end. So how these derivatives will work? Well, they depend on the dependency we have. Because if we start with a dependency on the velocities, then we need to take the derivative only once, and we already have something that depends on the accelerations. But if we start with something that depends on the positions, then we need to take the derivative twice to get something that depends on the accelerations. So let's start with the velocity dependency. So our error depends on V, and it has this specific form, y of V minus y star of t. And we want to impose the first order dynamics of the error. So E dot equal minus KE. Here we used a linear dynamics, but we could also make it nonlinear. It wouldn't change anything. The key point is computing E dot. So computing the derivative of this and showing that this derivative indeed depends on the joint accelerations V dot. So E dot is nothing more than Y dot minus Y star dot. So Y star dot, we have it here, and Y dot, through the chain rule, we can express it as the derivative of Y with respect to V times the derivative of V with respect to time. That's the same chain rule we have used even before. So this quantity here is nothing more than the usual Jacobian, just a Jacobian of a different function. And this quantity here are the joint accelerations. So we have recovered something that is a linear function of the joint accelerations, which is exactly what we wanted. We can move this Y dot star to the left-hand side. And so we can see even more clearly the linear dependency on V dot. Yeah, this is the same I was saying before. Instead of having minus KE, here I could have whatever function of the error E. So I could add saturations, I could have a polynomial feedback controller. It wouldn't change anything. What's important is that I have a linear dependency on V dot. The dependency on E can be even nonlinear. Okay. Even though I've been working my whole life with these linear feedbacks, and I've never felt I needed anything more. Maybe some saturation at most. You may need some saturation. if you have a scenario in which the error can get very large, you want to avoid then asking for a too large acceleration. Having some saturation on this error term would make sense, but it's not strictly needed, in my opinion. Okay. Second possibility is that your error function depends on the joint configuration Q. So in this case, we need to differentiate twice to get something that depends on the joint accelerations. And the dynamics that we need to impose is going to be a second order linear dynamics. Again, could be nonlinear, doesn't change anything. What we care about is figuring out the dependency of this E double dot. And well, the math is always the same. You just take the derivative once, you take it twice, you use the chain rule to express things through the Jacobian of the function y, and you get this expression jv dot plus j dot v minus y double dot star. And you can move everything which is not dependent on v dot to the right hand side, so it becomes clear that you have an affine function. Okay, and well, here I was just highlighting the fact that this is nothing more than a special case of the end effector control, which we have already derived before the break. And indeed, this should remind you of what we have seen before, the relationship between the end effector acceleration and the joint acceleration. These are almost the same expression. Okay, in case you have a dependency on U, you must have something affine. For a dependency on the state X, you can have something nonlinear, but you cannot directly impose that error because you don't have a dependency on the decision variables of your problem. So what you do is that you impose either the first derivative if you have a velocity dependency, or you impose the second derivative if you have a configuration dependency. So what you get in the end is an affine function of v dot and u. So here I'm calling z this vector that contains both the joint accelerations and the joint torques. So that's the vector of the decision variables of my problem. And I know now that I can represent my cost function as an affine function of z. Okay. And in this way, I have generalized the end effector control, which we have seen before. So now I can control whatever function of state, even nonlinear, and control just linear. And probably, yeah, I would stop here for today because we are almost out of time. And tomorrow we finish this pack of slides and then we move to the implementation. So try to come with your laptop and possibly with the code already up and running. If you have problems with setting up the system, you can send me an email and I will try to help you, or we can stop after the lesson tomorrow to figure out your problems or during the breaks.